Okay, so we'll continue on. There was a mistake. The green arrow should have been pointing over here because B was labeled delay, so delay goes on the bottom, so maybe you might want to fix the arrow in your notes. It used to be pointing over here, but now it is correct. All right, we will go on. In the textbook, there are a few exercises that you are responsible for doing and learning in section 3.3, and that deals with using a table to calculate given and conditional probabilities. I think it's quite straightforward that I don't feel like I need to dedicate a whole lot of or any lecture time to it, because it's just kind of like looking at a table and dividing the proper cells. Again, if there's any questions or hesitation, don't hesitate to ask. So, but I think it's straightforward enough that you can do it. And also there's a section 3.4 dealing with density curves. And the idea with the density curve, the main point with section 3.4 is that the total area under the curve adds up to 1. I guess it's worth writing down here. So section 3.4 with density curves is that I guess the most important thing is that the total area under the curve is equal to 1. Okay? Total area under the curve is equal to 1, and from there everything else is based on that. And so to find out the probability of being within a certain section of the curve or certain section of the number line corresponds to how much area that section takes up. Okay, and again, you got a couple exercises in the homework in there, or just one exercise. And again, I think it's straightforward enough that you guys can do the reading, figure it out, and it'll be clear. So I want to move on to section 3.5, which covers random variables. Now, I guess this is where we're dealing with numeric variables, and I guess there is a difference in how we do things if it's continuous versus discrete. But in our class, we're only going to cover the discrete case because the continuous case requires calculus, and but it's similar in concept anyway. But we're not going to cover the continuous case. We're just going to cover the discrete case. So anyway, what is a random variable? Okay, so a random variable, and why are we dealing with them in the section of probability? So a random variable is the outcome to a random event expressed as a number. Or maybe expressed isn't the right word, sorry. A random variable is the outcome to a random event and recorded as a number, I should say. Okay, and so let's say your random event, and I guess when it's recorded as a number, it should also make sense as a number, okay? So the random variable as a number should also kind of make sense, and not just this arbitrary, we're assigning different cases to numbers, okay? So should sort of make sense as a number, okay? So what counts as a random variable could be we flip a coin, or we roll a die. We'll start off there. We roll a die. What number appears? Okay, this is a random variable. Okay. Another case, we flip a coin, and we can say, how many times did it land on head? Times does it land on heads? Okay, so when we roll a die, what number appears? The outcomes are going to be 1, 2, 3, 4, 5, 6. If we flip a coin one time, how many times does it land on heads? It's going to be 0 or 1. Okay, so essentially we're just turning the outcome heads or tails into a number 0 or 1. Okay, but it makes sense because we can ask a question where it kind of makes sense. Okay, so not a random variable would be, you know, pick M&M at random. What color is it? That would not work for random variable because the outcomes are, you know, red, orange, yellow, green, blue, and brown. Okay, and you can't. There's no way to assign numbers to these cases in a way that makes sense in a non-arbitrary fashion. Okay, so I mean, we could try to assign numbers to these, but it would not. Whatever numbers we assign would feel arbitrary. Okay, if somebody says red is assigned the number 1 and yellow is assigned the number 2 and green is assigned the number 3, somebody else could say, well, I want to assign green to be number 1 and blue to be 2 and brown to be 3, and both of those things would be okay. So this doesn't count as a random variable. Okay, so the random variable is the outcome to an event, and that outcome is a number, or recorded as a number. So heads and tails, it kind of makes sense if we ask how many times does it land on heads, 0 or 1, okay? And you know, if we wanted to do males and females, we could say, you know, how many Y chromosomes do you have? And it's either going to be 0 or 1, okay? And so it can kind of make sense at some level here, okay? So perhaps more. So these are examples of random variables. We can also do. So these would be discrete cases. Another example of a discrete case would be we select someone at random. We select a person at random, and we ask, you know, how many children do you have? Okay, and you would get some answers: 0, 1, 2, 3, etc., etc., etc. You know, up to, I don't know what the limit is on how many children someone can. Well, I guess if you are a Genghis Khan, you can have 1,000 children, right? So, okay, so whatever number, maximum limit. Okay, so it continues. Okay. We can also have continuous random variables. So these are all discrete, but we also have continuous random variables. But we will not study these in detail today. This could be we select a person at random. And we ask, how much do you weigh? And that answer can take on any value, right? And it's continuous because someone could say I weigh 136.12 pounds, and someone else can say I weigh 136.157 pounds. And, you know, for practical sense, we can say they're practically the same weight, but if we have accurate scales, these are different weights. Okay, so continuous variables can also be expressed with random variables. But and again, the important part is that there is a random component to it. If you're just recording numbers or something, and there's not a random element, it's not a random variable. Okay, so a random variable, there is a random element. We're doing some kind of random event, and that the outcome of that event is a number. So rolling a die, flipping a coin, all of these things. This is these are random events. Okay, so when we talk about random events, we might have what we call the expected value of a random variable. Okay, and the expected value, we would write E of y, okay? If the random variable is y, so the random variable y, the expected value is E of y. This is also known as the mean of y. I should write capital Y, mean of y, and it can also be written this way with the Greek letter mu of y. Okay, so these are all equivalent ways to write the mean or the expected value of a random variable, y. Okay, and so what is the mean? The mean of a random variable is if we were to repeatedly do these random trials over and over and over and over again, and every single time we record the outcome as a number, and then we took the average of all those numbers we recorded, what would the average be? That is the expected value or the mean of a random variable. Okay, so the mean of y can be thought of as if we repeat the random trial many, many, many times, and we record the outcome or the random variable each time, and then take the average at the very end, take the average or mean of all our observations. Then that is the mean of y. That is the mean of y. Okay? So for example, let's say we flip the coin a bunch of times. Flip a coin, okay? And we say the random variable is such that heads equals 0 and tails equals 1. And we just get, a sequence: heads, heads, tails, heads, tails, 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 heads, tails, etc., 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 etc. And we record, okay, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1. And we have all of these numbers, and we take the mean of all of our observations. observations, okay? Then after an infinite or near infinite number, the mean we get would be the expected value or the mean of the random variable, okay? The mean we get after, you know, a near infinite number of trials is our mu of y. Okay? So what would the expected value of this random variable be? Flipping a coin. What would so if we have, you know, we've defined a random variable this way, right? Like basically flip a coin once, how many tails do you see? How many tails after one coin flip? Right? So what would the expected value be? It's the average of all of these things, so our expected value would be 0.5, right? The expected value of y, or the mean of y, is equal to 0.5. So, you know, on any one coin flip, you're not going to get 0.5 tails. You're either going to get 0 tails or 1 tail. But if we recorded this every single observation after thousands and thousands or millions or billions of trials, the average of all of those records should be very close to 0.5. Okay? Is that okay? And this we can make it more complicated, okay? So let's so let me just copy this table from the textbook. Where is it? Here it is. No, that's not what I wanted. I wanted snipping tool, not... Okay. Alright, so let's copy this. Alright, so this is some species of fish. I forget what species it is. Fish vertebrate Cottus rothius. I'm gonna look this up because I'm curious now. Cottus rothius. Let's see. Homework solution. Oh, somebody. These are all the answers. Oh, that's all. It's all the homework problem. This is. Okay. Yeah, I know. It's Cottus rothius fish. Let's see. Okay, there we go. This is what it looks like. That's excellent. All right. So apparently, when you you open up this fish, they can have different number of vertebrae. All right. So I think, do humans have different number of vertebrae? We all have the same number, right? Like we should. But apparently for this species of fish, they don't. Okay. The giraffe has the same number of vertebrae in their neck as humans do. You know, so they're just much longer. Just okay. Anyway, so apparently the fish, you know, most of them have either 21 or 22 vertebrae, but you know, some only have 20 and some have 23. But apparently there aren't any fish outside of this range. Okay. So the question is, what is the average number of vertebrae? Okay. What is the mean number of vertebrae in this species of fish? Okay. So we have a distribution here, okay? it says 20%, 3% of the fish have 20 vertebrae, 51% of the fish have 21 vertebrae, 40% of the fish have 22, and 6% of the fish have 23, okay? It's important that we do not do this, okay? Do not do 20 plus 21 plus 22 plus 23 divided by 4 equals 21.5. That is not correct. This assumes that each of these things show up equally likely, and that's not the case. Okay, so this only works for samples of data. Okay, so just this is what we're doing. Sample sum of y over n only works for samples of data. Okay, here we are dealing with a random variable. Okay, so random variable, the expected value of y, or the mean of y, mu sub y, is equal basically the weighted average. So we're going to take each value and we're going to multiply it by the probability of taking on that value. Okay, this is what we're doing. Okay, so this is essentially a weighted sum. Okay, we are weighting each possible value by its probability. Okay, so in this case, we can have 20 vertebrae, but that only happens 3% of the time, so I'm going to multiply it by 0.03. We can also get 21 vertebrae, and that happens quite a bit. I multiply that by 0.51, and then I do the same for the other values. Okay, and if we go through this, you know, coincidentally it ends up very close to 21.5, but it's not exactly the same. But let me just show you. 20 times 0.03 plus 21 times 0.51 plus 22 times 0.4 plus 23 times 0.06. And I get 21.49. It's just a coincidence that this value is very close to this, but they are different, and you cannot expect that doing this will give you something very close to the real thing. That happened to be the case with our data, but not always. So this is our expected value or mean of this random variable y. Okay. So this is the formula you need to know for that. I don't know what's going on there. Okay. So let me also do the standard deviation, or the variance. Let's do the variance, okay? So the variance of a random variable, okay? So the symbol for variance is sigma squared sub y. So the variance of a random variable is also similar, except we are calculating basically the weighted average squared distance from the mean, okay? The weighted sum of the squared distance from the mean. So the variance of y is given by this formula. We first have to calculate the mean of y, and we're going to take each value of y and subtract off the mean, and we're going to square that distance, and then we weight that squared distance by the probability, okay, and then we add those up. So maybe I'll draw a box around this to indicate also an important formula. Okay, so let's let's do it for this. Okay, so we're going to take each value, and we're going to do 20 minus the mean, 21.49. We square that value, and I'm going to multiply it by the probability of getting 20, which is 0.03. And I do this for each one. 21 minus 21.49. Square that distance, multiply it by the probability of getting 21. And I do the same for the other values. Okay, and so we can see that this gets pretty tedious with more than a few outcomes. But there might be, or there will be, an exercise or a question on your quiz asking you to calculate the mean and variance or standard deviation of a random variable. But I'll have at most 3 or 4 rows here, okay? You know, you could imagine if somebody had 10 different outcomes, it would be quite painful to do all of this, okay? So anyway, I'm not going to do this right here, but you punch this into the calculator and you get 0.4299. If you do all of this squaring and multiplication and adding, you do that for all these different values, it adds up to 0.4299. So then if you wanted the standard deviation, that would just be sigma y. You take the square root of 0.4299 and you get 0.6557. So that's the mean and the standard deviation of a random variable. Okay. So again, over here, it is the idea of we are going to just select or catch one of these fish at random, if that's possible. We catch a fish at random, and if we were to record how many vertebrae over and over and over again after all these different random catches, how many, what would the average be? That average would be 21.49. Okay? And if we were to do the standard deviation of all of those things, we would get 0.6557. Is that okay? Okay, let's, how much time do we have? Okay, let's just try a simple example with a random variable. Do I want to do this? No, let's skip this. Okay, so you're just responsible for basically doing doing this. Okay.
Stuff on next week's quiz?
Yes. Okay. So you have exercise in your homework like this, and you can expect a question in your quiz looking something like this, and it won't be any more complicated than this. Okay, so I think in the interest of time, I'm going to just go into the binomial distribution. Okay, so we have a special random variable called a binomial random variable, or also known as the binomial distribution. So, the binomial random variable, like any other random variable, is the outcome to a random event or random trial recorded or expressed as a number. So, but these all follow a certain form or certain pattern, okay? And they all say something along the lines of you're going to do some random trial or some random thing n times, and out of those n times, how many times will you get j successes? Okay, or what's the probability of getting j successes? So, for example, let me list off a few examples, and then I'll put the general form. Okay, so examples of random binomial random variables. Okay, examples. Flip a coin 8 times. What is the probability the coin lands heads exactly 3 out of 8 times? Okay, or shoot a basketball 10 times. What is the probability that you make the basket exactly 7 out of the 10 times? Okay, or I don't know, select 15 random people. What is the probability that 6 of them have type O blood? Or something like that, okay? So they're all in the form of do a random thing n times, and we ask what is the probability that we observe j, and we just call them successes, okay? The label success is an arbitrary label. Not necessarily, we associate success with a good thing and a bad thing, but here it's just whether something happened or didn't, okay? So in this case, type O blood would be considered a success, and people who don't have type O would be considered a failure or a non-success. But again, that's an arbitrary label, okay? And so, you know, if we were to say, you know, what's the probability that 6 of them have some disease? In that case, the disease would be considered the quote-unquote success, even though that's not generally how we would use the word, okay? There's a critical assumption, okay? Key assumption, and that is the probability of a success, again, in quotes, the probability of a success is the same for every single trial. Yes, question?
So it seems different, with all due respect, to the second one about shooting a basketball, because if it were me shooting a basketball, it may be, you know, to get 7 out of 10 would be a lot, you know, would be a big deal. By probability might be lower than 7. Do you know
So,
or if you're better at basketball, whereas flipping a coin seems more.
So okay, so we'll cover this. So perhaps, you know, yeah, I am terrible at basketball. So what is the probability that I would shoot exactly 7 out of 10 baskets? It's probably going to be very close to 0. Okay, the probability of a success for one single trial is not whether that's high or low doesn't really matter. The key is that the probability is the same for every single trial. Now, this basketball one, that might be this key assumption might not be true for everyone. Okay, so if somebody, you know, I guess if it's like a, I don't know, a machine that just kind of throws with some kind of consistency or something, but I don't know, there's just random things going on, then maybe it will or will not go in. I don't know, if somebody has to shoot a basket, 10,000 times, there's probably a chance that fatigue would set in, and maybe the baskets towards the end would not have the same probability as the baskets in the beginning. But again, if we're just assuming that the probability of a success, whether that's making the basket or flipping the coin or whatever it is, remains the same for every single one of these trials, then it counts as a binomial random variable. Okay.
So if I'm the one shooting the basket every single time.
Then as long as your probability is the same, then it counts, okay? Now if you were, I don't know, some guru that as you shoot more baskets your skill improves or something, then it's no longer a binomial random variable, okay? The key assumption is that the probability of a success is the same for every single trial. If that holds true, and it's kind of in this form of you're doing this random thing n times and you want to know the probability of getting j successes, then it's a binomial random variable. Okay, so this shooting a basketball, as long as the probability of making a basket is the same every single time you take the basket, all 10 times, then it's still a binomial thing. Is that okay?
I guess. I'm a little confused with this.
Okay, if we don't like this basketball one, it's okay.
Well, no,
it's
even the blood type one. I'm just trying to equate them, but it's okay. I'll read on it. It's okay.
So with the blood type one, we're just going to assume that the general population, let's say, is it's like 45% type O blood. Okay, something around there. Okay, so if I pick a person at random, okay, I don't know how to pick someone at random, but if I did, what's the probability that this person has type O blood? It should be 45%. And if I pick another person at random, what's the probability that other person has type O blood? Should also be around 45%. Okay? As long as I'm not picking people in the same family or things like that, the probability that someone has type O blood should be around 45% every single time I pick someone at random. Okay? So that key assumption is met, and it fits the form of we're doing a random thing n times, and what's the probability that we get j successes? It goes that way. Okay, so let's just try answering this type of question with the tools that we already know, and then I will illustrate to you how the binomial random variable formula kind of simplifies this work. Okay, so let's say 45% of USA has type O blood. It's something around there. I don't know. I'm making this number. I think O is the most common. No? A. I gotta look this up now. Type O blood. I don't know. Frequency. Let's see. Blood types. Oh, now I have to deal with RH factor. Okay, we're just gonna say type O blood is 45%. Even if it's not true, let's just say for the sake of this example, it is. Okay, so let's say 45% of the USA has type O blood. We will pick 4 people at random. Okay, and we want to know what is the probability that 2 of the people have type O blood. So I'm going to start off by drawing a probability tree. This one is the first person, and this person can have type O or not O. And this person has type O with probability 0.45 and not O with probability 0.55. Okay? And then we go to the second person, and we go O, and I'm just going to write O and NO for no. Okay, and we have 0.45 and 0.55, 0.45, 0.55. Okay, and I'm not going to bother labeling all of these out, but we're going to have 4 levels of this. Something like this, right? And so we have a total of, I got it, I'm going, no, that's going to take too long. Okay. So I can go through and label all of these things, but we can see it's going to be 0.55, you know, there's 16 possible sequences, right? This top one is, you know, O, 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 and this one is O, 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 not O. And then this, you know, this one would be O, O, N, and N, and then O, O, and then O, O, and N, and so on and so forth, okay? There's 16 arrangements. Okay? Can we see that? And so to answer this, I would have to find all of the ones that have exactly 2 O's. Okay? And I can list them out here, but they would go something like this. O, 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 N, N, and then I would have O, N, O, N, O, N, N, O, and then, how does it go? N, O, O, N, N. I think that's all of them. Did I get them all? Yes. Okay, so there are 6 ways to have 2 O's in 4 people. Is that okay? All right. What is the probability that we get this first initial sequence? No. And that's actually not 1 out of 16, because these don't have equal probability. Okay. So to get OONN, okay, so what is the probability of OONN?
1 out of 6.
It's going to be 0.45, because we're going to pretend like we're going down the tree multiplying, okay, times 0.45 times 0.55 times 0.55. Can we see that? Okay.
So you have to multiply the entire sequence.
Yeah, you have to multiply the entire sequence.
Because it's weighted. It's not.
No, there's no weighted in this one, okay? So each path.
Across the tree.
Yeah, we're going down the path in the tree. Okay, so this one, the first path, you know, I don't know. It's going to be O, O, no, no. Okay, and the next one will be O, no, O, no. Okay, and then so that one, probability of O, then N, then O, then N, would be what? 0.45 times 0.55 times 0.45 times 0.55. Okay? And then I'm going to just do one more just for the sake of illustration. And then this one, O, N, N, O, would be 0.45 times 0.55 times 0.55 times 0.45. Is that okay with everyone? Okay? Now, what do we notice about all of these things? If I multiply this out, they would all be the same, right? Because we know multiplication, the order of the things that you multiply, it doesn't matter. It's all the same. And all of these have 2 O's and 2 N's. Okay? So essentially each of these, each one, each sequence with 2 O's and 2 N's is going to be 0.45 squared times 0.55 squared, right? So every single one of these will have the same probability of 0.45 squared and 0.55 squared. Okay? So this total probability, the total probability of all 6 arrangements will be equal to 6 times 0.45 squared times 0.55 squared. So I know you see that, but I just want to make sure everybody else can see that as well. Okay, and so we can use this fact to avoid having to deal with this tree where there's 16 paths to calculate, and if I said I'm going to pick 10 people, then there would be 1,024 paths to calculate, and we don't want to do that. So so we're going to use this, and we're going to say that if we have n trials and we are looking for j successes, okay, and the probability of a success for one trial is p. Then what we have is here, let me just cycle back and just kind of copy this so we can kind of see where this is coming from. Actually, let's copy this first. So we've got this. And let's get this piece. Okay, so we have this. So the general form is we're going to take the probability P, the probability of a success P, and raise it to the J. Okay, so that's going to be the 0.45 squared. Okay, we're looking for J successes, and the probability of a success is P. So we do P to the J. But that means if we have a total of n trials, how many failures do we have? N minus j, okay? And if the probability of a success is p, then what's the probability of a failure? 1 minus p, okay? So we're going to have 1 minus p raised to the n minus j, okay? So we have j successes, j success. We also have n minus j failures. Okay? So each sequence is going to have the probability p raised to the j times 1 minus p raised to the n minus j. Okay? And so the last part is how many sequences do we have? Okay? And when we listed them out, we found that there were 6 ways to get 4 people with 2 type O's. Okay? But, how do we get that? Okay? Well, that one comes from the binomial coefficient, which we write n choose j. Okay? N choose j can also be written n this way, n choose ncj, and it's read as n choose j, and this is also known as the binomial coefficient. It is the answer to, if I have 4 people, how many ways can I arrange it so that 2 have type O, okay? Another possibility is, you know, if I have 4 people and I need to pick, select 2 of them to be representatives, how many ways can I get 2 representatives from a group of 4? Okay, and so that's 4 choose 2. Okay, and 4 choose 2 is equal to 6. Now to calculate this, if you have a calculator, you might have this little function over your divide sign that says NCR. Okay, depending on your calculator, if you have a TI, it might be under your math or probability menu. If you've got one of these Casios, you can do 4 and then you hit shift divide sign to get NCR, and it just shows up as a C for 4 choose 2. And when I hit equals, it tells me that's equal to 6. Okay. And also in the back of your textbook, in the reference tables, there's the binomial coefficients, and you can go to the row 4 and the column 2. I don't know if you guys can see this. So if I go to the row 4 and the column 2 for n choose j, we see that that's also equal to 6. Okay, probably don't need to zoom in that much for n choose j. Okay, there is a formula using factorials, and it's n factorial divided by j factorial times n minus j factorial, but you don't have to bother with this, okay? If you've got a calculator that can do n choose j, just use it, okay? And it just represents how many ways can you arrange j successes in n trials. That's the answer to that question. N choose j. And so the probability of getting j successes is n choose j, p to the j times 1 minus p raised to the n minus j. Okay, so does it make sense with how we got to this point? Okay, I don't feel like I need to explain this, and I'm just going to say just use this n choose j thing. You don't have to worry about this formula here. If you want to stay after class and learn, we can spend time doing that, but it's like a 10-minute explanation that, to be honest, it's just easier to just punch it in the calculator and it's not as necessary to know. Okay. So we arrived here. Okay, so let's just do a sample problem and just check our understanding. Okay, so let's say the probability that someone has type O blood is, we'll say 45%, okay? And we will say we will pick 8 people at random, okay? What is the probability that 5 people have type O blood? Okay, so go ahead and take a minute to figure that out. How are we doing? Mm-hmm. Yeah, exactly 5 people. I think I did my math correctly, but I'll check. 8, choose 5. Okay, so I'm just plugging in our values here, okay? So when we read our problem, we pick 8 people at random, so n is equal to 8. And we are looking for the probability that exactly 5 people have type O blood, so our j is equal to 5. And the probability that someone has type O blood is 0.45. So I have n, 8, j, 5, and p equal to 0.45. So I'm going to do 8 choose 5 times p to the j, so the probability that someone has type O blood is 0.45, and I need 5 people, so I'm going to raise that to the 5th power. The probability that someone doesn't have type O blood is 1 minus 0.45, and if I have a total of 8 people and 5 of them have type O, then that means 3 don't have type O. And so I have 8 choose 5, 0.45 to the 5, and 0.55 to the 3. So if I do 8 choose 5, I get 56. And I'm going to just do 56 times 0.45 to the 5 times 0.55 to the 3. And I think, yeah, I should get, so 0.45 to the 5 times 0.55 to the 3, I get 0.1719. So 17% chance that if I'm picking 8 people at random, 5 of them will have type O blood. Okay? And so we can use this to answer, more complicated questions. What's the probability that 4 or 5 people have type O blood? Okay, so if I ask that, I'm not going to go bother with the math, but we'll say, what is the probability that 4 or 5 people have type O blood? Then we would just do the probability that j is equal to 4 plus the probability that j is equal to 5. Okay, so this would require 8 choose 4, 0.45 to the 4, 0.55 to the 4, plus 8 choose 5, 0.45 to the 5 times 0.55 to the 3. Okay, and we already found this number to be 1719, and then the other number, whatever that is, we add those two together. Is that okay? So I didn't bother going through all the steps with this calculation, but that we can use this sense to do something like that. Okay. If I said, what's the probability that at least one person has type O blood? How would we go through that? So if I said, what is the probability that at least one has type O? Okay, well, one way to do it would be tedious, but I would have to do probability that j is equal to 1 plus probability that j is equal to 2 plus probability that j is 3 all the way up to probability that j is 8, right? So that's one way to do at least one. I said at least one is equal to the complement of what? Of getting 0, right? So you either got 0 or you got at least 1. That's That's it. For the rest of your life, you're either going to get 0 of something or at least 1 of something, okay? There's no other possibilities, whatever you're talking about. So instead of having to do 8 calculations in 8 numbers, I could also say this is equal to 1 minus the probability that y equals 0, okay? And doing y equals 0 is just one calculation, and that's not too bad. It's going to be 8 choose 0, p to the 0, and n minus p, or I'm sorry, 1 minus p to the 8, okay? So whatever it is, okay? And so that 8 choose 0 is 1, and all of these things simplify. So it makes your life easier. Okay. So treating something, at least 1, as the complement of 0 can also make your life easier. Okay.
Factorial of 0, 1.
Yeah, the factorial of 0 is 1. Okay, it's a strange thing, but the factorial of 0 is 1. Yeah. Yeah. You can look that up. Why is the factorial of 0 1? And you might find a nice video on that number file or something. Okay. Okay, so with the last bit. So remember, binomial variables are still random variables, and so we can still have a mean and a standard deviation and a variance, okay? Now, for binomial variables, there are shortcuts to calculate these things, okay? So the process for finding the mean of a random variable, you had to do, the weighted sum of y times the probability of getting that value y, okay? But for binomial, if you go through all of this math, it just simplifies to n times p, okay? And, for the standard deviation, it would be the square root of this whole thing of, y minus mu squared times the probability of y, okay? But again, for the binomial, it just simplifies to the square root of n times p times 1 minus p. Now, we could go through the derivation of all of this, but we don't have to. Just, it's sufficient to know that the mean is n times p and the standard deviation is this thing, okay? And the mean actually makes intuitive sense, okay? If we're selecting 100 people at random and 45% of the general population has type O blood, if I select 100 people at random, how many people would you expect to have type O blood? 45% of 100, or 45, okay? And so that's all you're doing. You're just doing 100 times that probability, 0.45, and you're getting that number. And of course, whenever you select 100 people, you might get 45 people with type O blood, but you might get something different. You might get 47 with type O blood, or you might get 40 people with type O blood. But if you were to repeatedly take samples of 100 people and count how many times you got type O blood, and you took the average of all of those different instances, I don't know if you worked at the Red Cross and every single time you got 100 people and you said, well, I don't know, in some weird scenario where you're repeatedly taking samples of 100 people and counting how many people have type O blood, the average of all of those different samples will approach this mean of 45, which is what we expect. Okay? All right, so that wraps up today's lecture, and we will see you guys next week for a quiz, and all of the details for that are on the class website.